All right, let's dive right into this explainer. We're taking what is usually a massive, overwhelming organic chemistry chapter and turning it into your ultimate high-yield visual study guide. If you're prepping for exams right now, you are absolutely in the right place. We're going to break down those complex mechanisms, map out the synthesis pathways, and, most importantly, identify those classic traps that literally steal points on test day. Here's the game plan for today. First, the carbon-oxygen anatomy. Then, physical properties and acidity. Third, mastering the synthesis trees. Fourth, key reactions and cleavage. And finally, commercial giants and a quick summary. So kicking things off with Section 1, the carbon-oxygen anatomy. You know, chemistry isn't just something stuck on a chalkboard. It is literally all over your house. These carbon-oxygen frameworks completely define our reality. They're the blueprints for pretty much everything you interact with daily. The paper in your notebooks, the cotton in your favorite shirt, the rubbing alcohol in your medicine cabinet, even the fragrances on your shelf. Once you understand these bonds, you actually start to understand the materials that build our entire world. Now, check out how we can visually break down the basic structures and their naming conventions side by side. The core differences are actually pretty straightforward once you see them like this. Alcohols had that OH group attached to an alkyl chain, which we write as R-OH. Phenols, same OH group, but attached directly to a benzene ring. That's your AR-OH. And ethers just drop the hydrogen entirely, bridging an oxygen atom right between two alkyl or aryl groups. That gives us that classic ROR structure. Okay, here's a crucial point before we even think about touching chemical reactions. You absolutely have to master these sp3 hybridized attachments. You've got to be able to categorize your alcohols into primary, secondary, or tertiary structures in your sleep. Why? Because this one simple attachment completely dictates how the molecule is going to behave later on. For instance, a tertiary alcohol is going to stubbornly resist reactions that a primary alcohol jumps right into. Moving right along to Section 2, physical properties and acidity. You will definitely see this classic setup on your exams, comparing molecules with near identical masses. Think about butan-1-ol and ethoxyethane. Even though they weigh almost exactly the same, the alcohol boils at a drastically higher temperature. It all comes down to those extensive intermolecular hydrogen bond networks acting like molecular superglue. Alcohols stick together incredibly tightly, so you need a lot of heat to pull them apart. Ethers, on the other hand, don't have that hydrogen bonding at all, so they behave much more like simple, easy-to-boil alkanes. Now, when we look at the acidity spectrum between these groups, I want you to burn this massive number into your brain: 1 million. Phenol is a literal million times more acidic than ethanol. That is a staggering difference. And as a quick rule of thumb for your tests, remember that electron-withdrawing groups on a ring will push that acidity even higher, while electron-donating groups will drag it down. But you might be wondering, what actually causes this massive baseline difference in the first place? Well, the secret is resonance stabilization. Think of the benzene ring kind of like a set of heavy-duty shock absorbers on a car. When phenol acts as an acid and loses its proton, the leftover negative charge isn't just stuck isolated on the oxygen atom. Instead, it delocalizes. It spreads out all around that aromatic ring, and because this resulting ion is so comfortably stable, phenol is just incredibly eager to give up its proton in the first place. All right, on to Section 3, mastering the synthesis trees. Think of this flowchart as your personal roadmap for alcohol synthesis. When you're staring down a tricky synthesis problem on an exam, trace it backward. You can reach your target alcohol from alkenes via acid hydration, from carbonyls through reduction, or by busting out the Grignard reagents. And speaking of Grignards, that pathway is extremely high yield for tests because your starting material dictates your product. Methanol gives you a primary alcohol. Other aldehydes yield secondary ones. And ketones, they'll snap together to give you a tertiary alcohol every single time. For synthesizing phenols, there are a few routes, but you really want to lock in on the global standard pathway down there. It starts with cumene, you oxidize it into cumene hydroperoxide, and then cleave it with a dilute acid. The beautiful thing here is that not only do you get your target phenol, but you also conveniently churn out acetone as a super valuable byproduct. Examiners absolutely love this specific dual yield reaction, so definitely star this one in your notes. When it comes to building ethers, the go-to is the famous Williamson synthesis. This is an SN2 reaction where a sodium alkoxide ion attacks a primary alkyl halide, perfectly locking that new ether bond into place. But you really need to pay attention here because there is a massive, classic exam trap lurking in this exact step. When you're trying to synthesize ethers this way, remember this rule. It relies on substitution. If you try to use a bulky secondary or tertiary structure, substitution is completely blocked. The reaction is going to stubbornly bypass your intended path and undergo elimination instead, leaving you with an alkane and totally wrecking your synthesis. Spotting this trap early is such an easy way to save crucial points on test day. Let's dive into Section 4, Key Reactions and Cleavage. This map is great because it highlights patterns you are going to see over and over. Dehydration removes water to form alkenes, and substitution swaps the OH to form alkyl halides. But look really closely at those oxidation stepping stones. This is exactly where those primary, secondary, and tertiary definitions from earlier come back to haunt you. Primary alcohols step all the way up to carboxylic acids. Secondary alcohols stop at ketones. And those bulky tertiary alcohols, they hit a brick wall and basically resist oxidation entirely under normal conditions. For phenols, your best bet is focusing your study time on named reactions. Take Kolbe's reaction, for example. By reacting phenoxide with carbon dioxide, we create salicylic acid. Now, why do we actually care about that? Because salicylic acid is the direct precursor to aspirin. So we're taking complex aromatic ring chemistry and connecting it straight to the household painkillers sitting in your medicine cabinet right now. Now, ethers are notoriously stubborn. They have this highly inert solvent shield, which makes them fantastic, unreactive solvents for other reactions. To actually break that carbon-oxygen-carbon bond, you can't just tap it. You need the chemical equivalent of a sledgehammer. And in this case, that sledgehammer is a super strong acid, like HX, applied with some really intense heat. Only then will that ether finally cleave apart into an alkyl halide and an alcohol. Bringing us to our final part, Section 5, Commercial Giants and Summary. Take a look at the stark contrast between our two commercial alcohol giants. Over here, we have methanol, often called wood spirit. It's synthesized industrially, used in things like paint varnishes, and is incredibly toxic. Even a tiny amount can cause blindness or worse. Then you have ethanol, the drinking alcohol you get from naturally fermenting sugars. Literally, just one extra carbon atom is the difference between a harmless fermented beverage and a deadly industrial solvent. Pretty wild, right? Okay, if you are struggling with time management right now, pause and take a screenshot of this summary table. This is your ultimate cheat sheet. It condenses this entire explainer into a single grid. You've got the core physical properties, the typical synthesis paths you absolutely have to memorize, and the major reactions for all three functional groups. Reviewing this table alone is going to save you hours of grinding through dense textbook chapters. This grand synthesis triangle is proof that organic chemistry isn't just a bunch of isolated facts to memorize. It's a connected web. The triangle maps out exactly how chemists fluidly transition between these three distinct molecular families. You can transform an alcohol into an ether using acidic dehydration, or jump from a phenol to an ether using that Williamson synthesis we talked about. As you review your notes and lock down these pathways for your exam, I want you to consider this final thought. Structure defines properties, and properties define function. It's an unbroken chain. By mastering the intricate anatomy of the carbon-oxygen bond today, you aren't just trying to pass a test. You're learning the exact rules needed to build the high-strength materials and life-saving chemistry of the future. So how will you use them? Good luck with your studies. You've got this.